All right, welcome back to the Protocol Town Hall, a periodic guest talk series focused on protocols and protocol research. In today's guest talk, we're speaking with Daniel Bashir about protocols and AI. Our next town hall will be on June 12th with author Kifan Chen. You can find out more about the Summer of Protocols, the program calendar for this guest talk series, as well as the protocol kit at summerofprotocols.com. And with that, I'll go ahead and hand it off to Timber to introduce our speaker, Daniel, today. Timber.
Thanks, Josh. So, for those that don't know Daniel, he's a machine learning engineer at Amazon Web Services, and he also does a bunch of other things like co-running the Gradient, hosting the Gradient podcast, talking with a bunch of interesting people there, and working with Clear Ventures as a fellow. Daniel, I believe you recently hosted Venkat on the Gradient podcast in
I
March.
did.
That was a super great talk. I definitely recommend people give it a
Thanks.
listen. There's some interesting overlap I gathered from that conversation between protocols and what's going on in the field right now with AI. Maybe they have a shared root in information theory or something like that. Anyway, I'm really looking forward to this overview of protocols and the AI landscape that you're going to give today. You want to take it away?
Yeah, let's do it. Well, thank you both. Thank you, Josh and Timber. It's great to be here, and I'm very excited to be talking about this intersection. So I'll first talk about maybe a few goals for what I'm going for here. I want to talk about protocols and AI as they intersect at a couple of different levels. And there are really lots of things to say here. Um, and I really think that there are many things that are done in AI at different levels, from funding to ML engineering to research to regulation. And all of these can be looked at from a protocol mindset. So I think it's pretty important to keep that in mind. Um, but to give you a sense of the goals and what I want to do here, I want to give you an introduction to some of the technologies, conversations, disagreements, debates, a little bit of the inside baseball of what's going on in AI right now. I want to talk about what current protocols or things we can cast as protocols in AI look like at the moment. And I'll aim to give you a little bit of an introduction, but there's a lot going on here. And as I put in the final bullet point on this slide, pretty much everything that we talk about could be an entire talk or talk series of its own. So I'll aim to give you a sampling, and I will give you some ways to reach me at the end in case you want to talk more about any of these things, or for me to point you in different directions. So to start, I feel like every AI presentation has to say something a little bit about the history, how we got here, what's going on. And I'll just very quickly rehearse a few of the greatest hits with you. The the era we're in right now, if we were to call it an era, is very much brought about by some of what happened, especially in the 2010s. But before then, there was a lot going on, what we call the pre deep learning era. People were still working on neural networks that kind of underlie the technologies we have today, but it looked very, very different from what we have now. And there's a lot here that deserves time to go into, but I won't spend too much time there. I think what's really most relevant to us is what came about later. And this is what we called the deep learning era. And this goes, of course, beyond just transformers and LLMs, but there was a very famous moment where a model called AlexNet came out of Geoff Hinton's lab that achieved a pretty high score on a benchmark for image recognition called ImageNet. And that was really what people identify as one of the key breakthrough moments for deep learning and where neural networks started becoming popular again. Many of us then saw the AlphaGo moment, which was very famously immortalized in a YouTube movie about what happened with DeepMind and beating the world's best Go player. So a lot has gone in since then. Many people have said different things about where deep learning is going. There's lots of debates around this, and we'll be talking a little bit about those. But I think right now, really, excuse me, we're in a moment that's been kind of precipitated by what feel like this technology, this sort of system that people were working on that didn't really seem to work. And then after people realized that if you train neural nets on lots and lots and lots of data, if you came up with a pretty simple general computation system like the transformer and threw a lot of data at it and scaled it up, then you could get something really powerful. And that's the sort of things we have today. So let's get a little bit into what protocols might look like for ML. And where I actually want to start, and maybe just to preface this, there's going to be a lot of directions and thoughts that I point out here and not a lot of prescriptions about protocols. I'll talk about different protocols that exist, but not necessarily weigh in. I might weigh in on what's sort of better than another. And I think that the way forward, I know that Venkatesh is very interested in having some of the folks involved in Summer of Protocols work on some of these things. So hopefully this will give you a lot of different directions and ideas that you can kind of start from. And where I think it makes sense to start is AI is a field that requires lots of money, especially if you're doing the sort of AI that looks like large language models. And the work of building AI systems is happening in pretty different places. I think it's pretty interesting to consider who should be doing what kind of work, because this itself is a pretty major topic of conversation in AI. So if you look at the government, for instance, DARPA has programs like the Modern AI Forward program, which aims to facilitate research collaborations for projects like autonomous AI scientists. The NSF has recently opened AI institutes. I think we all know what's kind of going on with the private sector right now and what some would call a psychotic amount of money that is being thrown at current systems. I think academia in particular is also just a very interesting place to look at right now, because there is plenty of work on language models, which seem to have seized the day. But when you're in academia, of course, you don't have nearly the same compute as industry. So an academic isn't going to be training a GPT-4 scale model, but you'll see smaller models they come up with that attempt to compete. You'll see new mechanisms for things like instruction tuning, which is what got us from GPT-3 to ChatGPT. And I think also kind of pertinent in today's landscape that a lot of people are thinking about is a question of what should an academic be doing in this environment with AI advancing as it is? And there's many, many different opinions on this. I'll pause on going deeper into that for now, but that's something that is worth thinking about. So the next main section of this talk I want to go into is a little bit about how we are building systems, and this is where protocols for doing research and engineering come in. And where I'll start is something that many people have kind of come to believe in or have different opinions about. Venkat himself definitely has some thoughts here about scaling, but one thing that I think has kind of come out over the past few years is these two themes: the scaling hypothesis and the bitter lesson. The bitter lesson is something that the reinforcement learning researcher Rich Sutton wrote about in 2019, where he said general methods, so search and learning that leverage computation, are ultimately the most effective. So what many people take this to mean is a general method like the transformer architecture, for instance, that doesn't have a lot of pre-built biases into it. When you apply a lot of computation, a lot of data to it, it's going to end up being pretty powerful. The other related point to this is about scaling laws. And the most brute version of this is you take a general system, you scale it up massively, you make a very large model out of it, you throw a bunch of data at it, and you get something kind of powerful. Now, when it comes to casting this as something like a protocol, there's actually more prescriptive versions of this. And you can think of scaling laws as a sort of protocol for training large language models. So this would seek to answer questions like, what size of model should you use, how much data should you use, and so on. So for an example of this, DeepMind researchers a few years ago trained a model called Chinchilla, and they developed what are now called the Chinchilla scaling laws. And this is basically a protocol for how do you develop a compute optimal language model. And what they found was, for the size of models people were training at the time, they could actually train them on much, much more data, and that would be more optimal given this particular compute budget. But it seems like that might not entirely tell the whole story. We've seen a lot of models coming out from Meta, and the Llama series of models, which have been open source, showed that you can take these models that are not necessarily super big and continue to train them on just insane amounts of data beyond what the Chinchilla scaling laws would predict. and continue to see improvements in their performance. So that's pretty interesting. And I think that's another kind of example of what a protocol can look like here. When it comes to how we think about scaling a little bit more generally, there are lots of different directions to consider when it comes to, is scaling going to work? What are the different aspects of scaling we should consider? And this is where I think the role of protocols kind of comes in a little bit too, because many people are thinking about, is scaling the right thing to do? Is it going to take us all the way? And this is always relative to a particular goal. As we know, many organizations like OpenAI, like DeepMind, have the stated goal of building something like an artificial general intelligence. Not everybody is convinced that that is a well-defined term. I think that there are definitions out there, and you could look at something like an encyclopedic or dictionary definition and have a sense, but not everybody agrees that that is what we should be aiming for. Not everybody agrees that AGI means the same thing. And a lot of people have just kind of resigned to not really having a definition of AGI. So this all kind of makes an impact on how people think about the state of the field right now, where we should be going, what scaling is going to do, what it means. But to put that aside for a moment and say that we are training these very large systems and we want them to get to something like human level performance across a maximally general set of tasks, maybe replace, maybe augment humans in lots of different ways, then we could look at some of the issues, the debates that are going on right now. One of the main ones is about the inefficiency of large language models. And what I mean by this is you have to train these language models on just a lot of data, a lot more than what a human would have to see, for instance, to get them to the same performance when it comes to being able to produce language. One sort of difference people look at is how child language acquisition seems to occur very, very quickly. But you have to train these LLMs on reams and reams and reams of text that no 4-year-old, no 5-year-old child is possibly going to have read. And people have different perspectives on what this actually means, whether that's a fair comparison or not. When I spoke to Venkat, he kind of cast this as all of the training data that an LLM is getting is actually just bringing it up to speed with humans. When it comes to humans have gone through this historical series of evolution, and we now have language that makes sense and all of these other things. So he kind of likened training, pre-training large language models to that evolution process. I'm not sure I'm entirely on the same page with him there, but I think that's an interesting perspective for it. There are a few different things as well that are kind of being debated, bandied about when it comes to new hardware architectures, alternative model architectures. I mentioned earlier that the language models we have today, they're based on the transformer architecture. And the transformer architecture is one that is known to have certain inefficiencies when it comes to scaling it up. And there have been lots of different directions explored with how can you make transformers themselves more efficient? How could we explore different architectures that are more efficient than transformers and bear the same capabilities? And these are all pretty different directions of research that have some initial promising results, but I think the jury is really not out yet on a lot of things. Another kind of clear protocol place that we're actually going to dig into a little bit more later is about benchmarks. And I think this is a particularly important one because when we're measuring up how good are the systems we're building, how good are large language models, that's always relative to what is it we're trying to get them to do. And I'm going to come back to this later, but this is just a sampling of different things people are thinking about. To double click on one in particular that I think is pretty important, my last slide mentioned alternative hardware architectures. An important point that many people raise right now is that GPUs and the transformer architecture are a very good match. GPUs are a hardware system that has a lot of parallelism built into the computation, and transformers are uniquely able to take advantage of that sort of parallelism. So you can see this as a good hardware software match. And a researcher named Sarah Hooker wrote a paper a couple of years ago called The Hardware Lottery that was essentially making the argument that the algorithms, the ML algorithms that have kind of won the day, they don't exist, they don't win in a vacuum, but they win because the available hardware that we have happens to be a good match for those algorithms. So this was very much the case with GPUs and transformers, but you could imagine an alternate reality where maybe the underlying sort of computation system or the underlying hardware was very, very different. And so a different set of algorithms happened to be a good fit for that hardware and therefore ended up being the thing that we built modern ML systems on. So that's one thing to consider. I think that we live in a world where when it comes to hardware, everybody does seem to be doubling down on transformers because that is where all of the interest is. But especially for people trying to compete with NVIDIA, this is pretty difficult. I included a photo here from the State of AI report where you can see that in AI research papers, NVIDIA chips are still kind of overwhelming and nobody really seems to be getting very close. Part of this has to do with the difficulty of building software stacks on top of these hardware systems so people can actually use them. But that's kind of another direction that people are thinking about a lot. I wanted to return to the idea of benchmarks and to give a few top level thoughts. When we think about benchmarks, these are measuring performance against some criteria, some set of criteria we might have. And they're kind of answering this question, how do we measure performance of AI systems? How do we know where we're going? How do we know we're improving? And that, of course, includes the question, improving towards what? What is it that we want? Do we want human-like generalization? Do we want AGI, whatever you will call it? Do we want something else? And so we have these traditional metrics that have been used to assess language models like perplexity, which you can think of as sort of an evaluation of a model's ability to predict uniformly among the set of specified tokens in its corpus. But when we think about, and maybe another way to put perplexity is it's kind of the confidence that the model has in its next word predictions. And the intuition behind that basically is that as a model performance metric, this tells us that a model's confidence basically correlates pretty well with its accuracy. And there's a drawback to that. We all know that large language models hallucinate and they're confident when wrong. So this is a pretty key shortcoming of perplexity. But I want to talk a little bit about more protocol-y versions of benchmarks. So perplexity is kind of one protocol for, I think that I want to measure how good language models are in a certain way. So I use this particular metric for it. But there's been a lot of conversation about benchmarks and what they should look like and how we should assess models and their performance and what we want out of them in the past couple of years. So I want to introduce two different ideas that have come up here. A paper I really liked was Tal Linzen's 2020 position paper about how can we accelerate progress towards human-like linguistic generalization. And he basically argues that this paradigm that we have right now, which he terms, and I'll break this down, I promise, the pre-training agnostic, identically distributed evaluation paradigm. He thinks that this kind of encourages progress in a direction that to him is sort of orthogonal to the goal of human-like generalization. And this is for multiple reasons. So it doesn't really consider sample efficiency. This is the pre-training agnostic part, and something that I mentioned earlier. LLMs, to get to the point that they are in producing human-like language, are trained on just a ton of data. And when we compare different language models to each other, at least a lot of comparisons that were being done when Linzen wrote this paper, they didn't consider the fact that some language models were trained on a few billion tokens of data, and others may have been trained on hundreds of billions of tokens or something of this sort. And so that seems like a pretty unfair comparison. So pre-training agnostic seems like not a good thing. The other point is that benchmark scores tend to be computed on test sets that are drawn from the same distribution as their respective training sets. This is identically distributed. And so Linzen's claim here is that this paradigm favors models that excel in capturing statistical patterns of particular data sets over models that generalize as a human would. And this is actually considered a kind of sin that you would see in your introductory machine learning classes. One thing that's often told is that you should not train on the test set. This is often likened to memorizing answers for a test instead of trying to understand the underlying concepts. And there are different directions to consider here, and that's maybe a little bit oversimplifying it when it comes to language models, because you are training on very vast amounts of data, where of course, you're not going to memorize every single word out there on the internet, but there are different directions and considerations of how much are language models memorizing versus how much are they distilling concepts. And there are many different sorts of results in different directions on this that have been pointed out. Um, and maybe a last point on benchmarks as protocols is a little bit about how we might think about measuring them qualitatively. So I've talked about what are mostly quantitative metrics at this point, but at the moment, a lot of people also care about what is it like to interact with these language models, with these systems. And so one thing that's become very popular is what are called vibe-based measures, where a lot of people will not entirely, but to an extent, maybe ditch going for a totally qualitative comparison or metric of how good is the language model I'm using and think about what do I want out of an interaction with the system? What should that look like to me? And so when Databricks was releasing one of their recent models, one thing their researchers talked about was the fact that what it was like to interact with their model was a pretty important vector for them to figure out how do we improve this sort of thing. So I want to return to the conversation about future directions in deep learning, because these are things that are pretty amenable to protocols. These are protocols about how to do research, how to keep improving systems. I mentioned earlier a lot of these things about how this is relative to objectives for the field, how there are questions about how far scaling is going to take us, whether we need new model architectures, whether we need new data. And I want to go over as kind of an example here the ways that different people have maybe come up against the sort of scaling that we're doing right now. So again, the kind of null hypothesis, the picture that we might be working with is something like GPT-7, GPT-15. That's going to be AGI, however you think about it. All we need to do is take the system we have now and just train it with more compute and more data. Maybe we need to make some modifications, but you could imagine a running belief that that is going to get us to AGI or something of that sort. And of course, that's vastly, vastly oversimplifying a lot of what's been said about this, but take that as something like your null hypothesis. Or maybe for an alternative version of that null hypothesis, that something like the sort of deep learning we're doing now, just trained with lots and lots of compute, lots and lots of data. So you're not thinking of very particularly smart algorithms or anything of that sort, taking Rich Sutton's bitter lesson. Something like that is going to get you what you want. And a lot of people disagree with this and have kind of countered with different sorts of protocols. And there are many different views here. So on this slide, I've talked about a couple. Francois Cholet, who developed the deep learning library called Keras, had a paper a couple of years ago called On the Measure of Intelligence that I'm going to do a dive into in just a second. Melanie Mitchell has a lot of thoughts on why AI is harder than we think. And one of the particular things she points out is that easy things seem to be hard. So things that seem easy for humans tend to be hard for AI systems, and hard things are easy. So things like image recognition tasks or other things that have been kind of difficult for humans, doing math, that sort of thing, that has tended to be easier for computation systems than we expect. And you can think of this as sort of something to do with the nature of human intelligence, with the nature of computation, and these being good at different things. So before I kind of dive into an example protocol for a different way that we might think about and measure intelligence, I'll dive a bit into Cholet's thinking about measuring intelligence and what that is. So for Cholet, he thinks that basically for coming up with a system that is truly intelligent, we need to have a stable definition of intelligence. And he actually introduces a formula for this in his paper, but he says something like the intelligence of a system is a measure of its skill acquisition efficiency over a scope of tasks with respect to priors, experience, and generalization difficulty. And a pretty key point here, you might think about that definition as a little bit anthropocentric, and the conditions under which intelligence tests have been carried out historically on humans aren't really easily transferable to computational systems. So Cholet actually thinks that this is kind of a feature and not a bug, and that really we should be thinking about measuring intelligence in these anthropocentric ways. he's very much kind of against what he calls the curve fitting paradigm or the deep learning paradigm, and that he thinks that curve fitting has some very key fundamental limitations when it comes to how intelligent such a system could get in his sense. And I'll try to refine this in the next few slides because I think there's a lot to say. So first, it makes sense to kind of introduce the hierarchies of cognitive ability as he imagines them. And so he thinks about generalization at these three different levels. One is you have very task-specific skills. You could think of this as a deep learning system identified for a specific task. That's an example of this, where you have kind of local generalization. It's able to do very well in that. You have broad cognitive abilities, and this might be over a set of tasks that are related in some fashion or another. So maybe you think of an LLM as something like this. And that's because it has this ability to do all of these different discrete tasks related to language, for instance. But what he's really interested in is that top level of the hierarchy, general intelligence or extreme generalization. So how do we actually get there? How do we build a system like this? Cholet thinks that to get human-like intelligence, which is the thing he's fundamentally interested in, you have to build in some assumptions. These are called priors, and this helps the system learn certain skills faster. And in deep learning, we often talk a lot about priors and inductive biases, and these have to do with the sorts of things an algorithm is more able to easily pick up. So to give you an example, in the deep learning world, convolutional neural networks have this sort of bias or inductive bias of translation and variance across images because of the way in which they process these images. And so that makes them a particularly good fit for doing image recognition. So when you're able to control the priors, then you can define what the system knows about its environment. And so in humans, these sorts of priors allow us to acquire specific sorts of skills very efficiently. And going back to the anti-percentrism point, Cholet thinks that this is legitimate and necessary because it's really the only scope that we as humans can meaningfully approach and assess. So he thinks about skill acquisition then as kind of a program synthesis. During its lifetime, a system is going to face many different situations. It's going to have to solve many particular tasks. And so it does this by generating a skill program, a program that is skilled in this particular situation. And when it produces a program that achieves acceptable performance in solving a task, then it's rewarded. And so the intelligence of a system for Cholet then is connected to its ability to generate sufficiently good task-specific skill programs for the given tasks. And so you can work this all out into kind of a mathematical definition. But what's kind of interesting here when you take this and think about measuring the intelligence of different systems is that the prior knowledge matters. He's kind of relativizing over these sorts of things. So if the prior knowledge of a system is particularly large, if you were to compare two systems and they both perform optimally at a particular task, if one has a lot of prior knowledge and the other has much less prior knowledge, and they both performed optimally at that task, then you consider the system that is a ton of prior knowledge less smart than the system with less prior knowledge. And this is, of course, because the system with less prior knowledge was able to more efficiently make use of the data that it's been given in order to perform well at that task. So diving back into something that's a little bit more explicitly a protocol, we've been talking a lot about benchmarks throughout this conversation. And one that Cholet presents for measuring intelligence is what's called the ARC benchmark, or the abstraction and reasoning corpus. And the sort of tasks here are ones that are solvable by humans generally pretty easily and should be solvable by a machine or system. And the tasks are inspired by something called Raven's progressive matrices. And this is a task in which the test taker is required to identify the next image in a sequence of images. And Cholet wants to do a lot of things with this. So relating to his definition of intelligence, Cholet wants to prevent brute force approaches where a system learns to exploit weaknesses in the data set. So the benchmark only provides a small number of examples for each task. And again, he makes the case that we should be interested in this sort of intelligence, where a system only presented with a few examples can generalize and perform pretty well in the task, because that's fundamentally what humans do. When you see these sorts of patterns, for example, and you're asked to predict the next pattern after seeing maybe 2 to 3 examples, you can generally do pretty well when you're asked to predict the next thing. So he thinks that a system like this, we should be able to aim for systems that can actually do this pretty well, in just as well as humans are able to do. And that's something that he would kind of consider intelligent. I think that maybe to give you a few questions to close this out with, though, before I move on to the next point. What I've talked about here is a particular protocol for assessing intelligence. And this seems like a decent protocol if you believe that intelligence has this particular definition and it should look this particular way, and if it makes sense to measure it like this. And these are all things you can question. You can question if Chalet is right about his definition of intelligence. Do you maybe think that's something else? And these are kind of all important questions to consider as you're assessing something like a benchmark, like a protocol for training these systems. The next thing I want to get into, we've been talking a lot about training, assessing systems. Another area where protocols kind of come more clearly to the fore is in actually using these systems. And so even if you think about ML systems that are not necessarily deep learning systems, they've come to be integrated in software in lots of ways. And we've seen a lot of cases where this has come out in systems that appear to be biased. For example, people have put AI systems into cases for predicting the risk of recidivism for released inmates, for example. And the fact that there are biases in these systems gives people a sense of, here are ways maybe we shouldn't use these systems. Maybe we should include humans in the loop. Maybe we should verify the results of these systems and kind of put them into a more holistic picture. So ML and software, there's a lot of different debates to be had about protocols for how you should integrate ML systems into broader software systems. In addition to that, there's a lot of technical questions. There are difficulties of integrating ML into software systems. The protocols for engineers themselves tend to look quite different. And so ML engineering is, of course, a job title that we've seen a lot recently. And the ML engineer title kind of tends to look different from place to place, depending on what it is trying to do. At the same time, you see a lot of opportunities and vulnerabilities and kind of modes of programming that come along with things like GitHub Copilot or AI that can write code for you. And so everybody is kind of finding themselves have to adapt in terms of, how do we work together with different engineers? How do we build these systems? How do we test them? And so the world for a software engineer has started to look quite different in a world where you're using these systems. I think that this is not too important. Another protocol related thing I wanted to go on to is about responsible AI. And so this has become a bit of a buzzword over the past couple of years. But when it comes to thinking about how we want to use AI systems, I brought up the point of using them to predict risk factors and things like this, especially when you're using ML systems in a way that could reasonably affect people's lives. It seems pretty important to consider how you're going to use those systems. Are we doing so responsibly? And there's a lot of concerns about the ways in which people use systems. Are they biased? Are they being used in correct ways? And so people are interested, reasonably, in developing protocols around what to do here. And many different things have come up here. So many people are interested in developing quote unquote fair AI systems. And the definition of fairness and what that means has itself been a topic of debate over many years. There was a line of research in ML that was looking at fairness from a pretty mathematical perspective. If your algorithm was trained in a certain way, if it satisfied certain equations, things like this, then you could call it fair for some reason or another. And eventually people started to think maybe that's not enough, because these systems are trained by people, they're embedded among people, they're being used by people. So you have to consider the full life cycle of these systems and what that actually looks like. I think it's also interesting to consider the questions of what a moral AI algorithm would be and what that looks like. And what's kind of interesting about ethics is that there isn't really a commonly accepted way of measuring the ethicality of an AI system. And there's a couple of papers out there that sort of argue that you can't really develop such a benchmark, and that maybe we should think more about values than ethics when we consider the possible actions of AI systems, which is another kind of interesting way to think about protocols for developing ethical systems, if that's something you're interested in. Another case for protocols here is about operationalizing responsible AI, which is a pretty difficult thing to do. So even if you have a conception of what it is to responsibly deploy AI systems, actually making that happen in the real world in an organization where people are going to have lots of different sorts of incentives, many of them are going to be business incentives, there's lots of other things going around. That becomes another area where you have to think pretty carefully about how are we actually going to do this? How do we develop a protocol for operationalizing this that is going to persist, that is going to do the sorts of things that we want. And you could think about different steps for responsible implementation. So Brookings, for example, thinks that if you have concrete codes of conduct, if you have appropriate operational tools for kind of promoting ethical principles, if you develop clear evaluation benchmarks and metrics, for instance, these are all steps you could take towards operationalizing whatever you might consider responsible AI. These are all pretty hard problems in and of themselves, but again, an area for people thinking about protocols to consider. So the last thing I kind of want to go into is a little bit about how we should be building systems, what it's going to look like, and a little bit more on the aspects of kind of deployments. So where I want to begin with this is a little bit about regulation. And this is a really kind of big picture thing. We were previously talking about operationalizing responsible AI, and this is something you might ordinarily think about at the level of a team of engineers, at the level of a company. But if we blow up the picture quite a lot larger, then at the level of nation states, at the international level, there are lots and lots of questions about how should we be allowing AI systems to be deployed. And there are lots of debates over whether we should have regulation, what good regulation looks like. And we can think about how we might approach protocols for this sort of thing, maybe beginning from the standpoint of something like political philosophy. And a lot of people think about this. Seth Lazar, for instance, is a thinker I really like who looks at how AI systems and computing systems impact what it means to be citizens, what it means to interact with other people. And this very much affects the kind of social contract we have with others. So that has a pretty important impact then on how we should do stuff like political philosophy, for instance. And that might be actually pretty important to you because when you're thinking about doing political philosophy and how you understand the impacts that these systems have on relationships between different people, on relationships between the governing and the governed, then that helps you think about what sorts of protocols we should have for governance and things like this. Because even when you're thinking about not necessarily governing the AI systems themselves, but how these AI systems embed interpersonal relationships, how people exist as citizens, for instance. That's a different world, and it maybe necessitates a slightly different set of protocols for how we ought to govern. I'll have a few examples of this in a moment, but another key point here is about defining policies around AI systems. And this is a bit about governing AI systems themselves. So many of the companies building these systems, developing them, OpenAI, DeepMind, for instance, have a pretty loud voice when it comes to maybe we should be regulating these AI systems and what that should look like. And many people are a little bit critical, and there's been questions about regulatory capture and things like this. And you might go one way or the other on this, but it does seem like different governing bodies, different countries are pretty concerned with developing policies around AI. And there's also questions you can ask around this: who should define these policies, who should implement them, who can implement them, at what level should policies regulate ML systems, and what sort of content should these have. So there are a lot of different policies that are at various levels of implementation flying around here. We have some in the US. The EU AI Act is one I'm about to go into. There have been pretty interesting, what kind of Matt Sheehan talks about as very large scale regulatory experiments going on in China when it comes to regulating ML systems. They've had laws come out on recommendation algorithms in particular, for instance, and these actually include all of these contents that I mentioned in that bullet point about disclosure requirements, about model auditing mechanisms, about technical performance standards. Again, lots of different protocols about what should be done here. But again, these are all difficult problems. They're impacted by incentives, by coordination problems, by race dynamics, by other issues. And so again, developing these protocols, you might have something that looks good, but you have to consider a level up. What is everyone else doing? And that's how a lot of people are thinking about all of this. So I want to take one case study, again, diving deep into a particular protocol and look at the EU AI Act. So to give you a kind of summary here, the most important thing to know about the AI Act is that it takes this kind of risk-based approach for categorizing AI systems. And so it operates at 4 different tiers, and you can see that in kind of the picture here. So at the very top, we have unacceptable risk. And examples of this for the EU are social scoring systems and manipulative AI. And these are just completely prohibited. Most of the text addresses what are called high-risk AI systems, and these are regulated in different ways. Then there are limited risk AI systems closer to the bottom that are subject to lighter transparency obligations. So, for example, people who are deploying the system should ensure that end users are aware that they're interacting with AI systems. And then we finally have minimal risk, and there's a lot of applications that kind of fall into this, like AI-enabled video games, for instance, and this is just totally unregulated. And there's a couple of important things to know about the AI Act. That, for instance, a majority of obligations fall on the providers or developers of high-risk AI systems. So if you want to place on the market or put into service these sorts of systems, then the burden is on you to meet compliance standards and things like this. And there have been a lot of concerns and criticism about the AI Act. A lot of people believe that this is actually holding the EU back when it comes to making AI progress. So when you're thinking about regulation as a protocol, there's lots of different things to look at here. You have to balance many different concerns. We want systems to be safe, but maybe we also care about the technological progress that our country or countries are making. And so there's a lot of different concerns to look at. When we think about different concerns that have been raised, one of the sort of fundamental ones is about the definition of AI that is proposed in the AI Act. So I pulled out the quote here, and it was initially defined as software that is developed, excuse me, with one or more of the techniques and approaches listed in the Act, and it can, for a given set of human-defined objectives, generate outputs like content, predictions, recommendations, or decisions influencing the environments they interact with. And a reason this was pretty concerning is that it didn't really provide sufficiently clear criteria for distinguishing AI from simpler software systems. And so presumably, if you've got an AI Act and regulation targeting AI, if you're going to define AI within that regulation, you'd better make sure that that definition not only is able to be sufficiently broad so as to encompass existing and future AI systems, or that you can easily update that definition, but also that if you're strictly interested in regulating AI, that your definition isn't so broad as to encompass other things that we don't think of as AI systems. So that's pretty important. The council has kind of suggested narrower definitions. So, for example, including things like designed to operate with elements of autonomy and other things like this. So there's ways in which they've kind of closed that gap a little bit. There's also different sorts of things that have come out here. So the boundaries for what constitutes a high risk system, excuse me, in the initial version of the bill were pretty unclear. People worry about the potential for stifling innovation that I mentioned earlier. And it's also not entirely clear how a system like ChatGPT, for instance, maps onto the different risk categories here. So there's lots of kind of unclarities going on with the sort of system. And so a lot of concern has been raised about it. But again, protocols, as Venkatesh talks about a lot, should be sufficiently evolvable. So when you're thinking about regulation as protocol, there's lots of if you're thinking about something like regulation, it's probably a good idea to go into different existing regulations, kind of understand how do they work, what are the concerns around them, where do they seem to be working well. And so if we were to look at a couple of different questions for people thinking about these sorts of things, and this is maybe where I'll end, a set of questions you could kind of pose to yourself for how to start thinking about these sorts of things is who should and can set these sorts of protocols. Excuse me. Another pretty important one is how do you put protocols together with the technological systems that they're designed around? So, for example, one thing that's often been proposed in regulations is sets of transparency requirements where governments might want to know a lot of information about how a model makes its decisions, how it's been trained. Excuse me. And a lot of these things are pretty difficult to do for AI systems. So, for example, interpretability is a whole area of research where people want to understand how these systems are working. But exposing all of that information can be pretty difficult to do. So there's a question about are AI systems designed in a way that makes their development and use amenable to certain sorts of protocols. Another one brought about by the EU AI Act, for instance, is how do you develop protocols that consider classic questions about issues like enforcement difficulty, potential hindrances to progress, and so on. And do you think you can set protocols in a way that appropriately manages those trade-offs? So that was basically what I kind of wanted to end with here. I think that as somebody who's thinking about protocols with AI, a good place to look is think about understanding how these systems seem to work, how people use them as engineers, as researchers, in the context of products in different ways. There are a lot of ideas being thrown about around regulation and how we use these systems. A lot of them have different strengths and limitations, and we're kind of seeing how this plays out right now. So I think that looking at those different strengths and weaknesses can be a good way to understand what could good protocols for developing, for implementing, for using these systems look like, and considering these different trade-offs, some of which are going to involve the use of AI systems, some of which are going to be a little bit broader. I think I'll leave you with this kind of set of questions to consider and there. So thank you a lot for listening. If you ever want to reach me, I have an email. I'm on Twitter as well. So if you have questions about any of the things I said in this talk, if you want to discuss anything further, because there's a lot to go into on all these various topics, you can reach me at these places. And I'll finish there. Thank you.
Oops, muted. Awesome. Thanks so much, Daniel. I appreciate your in-depth look into language models and AI and sort of the state of the art here. We can open it up. We have about 9 minutes left for questions. And I believe Timber's got one off the bat here. Go ahead, Timber.
Yeah, I was wondering if you feel like the current general efforts at regulation are striking a good balance between limiting things, like having not too broad or too narrow of definitions, or if you feel like there is one area where regulations are like completely failing in and like being way too specific, way too controlling, or if it's generally like it's within the realm of reasonable effort.
Yeah, that's a good question, and definitely a pretty hard one to answer. I feel like when it comes to regulation, I don't know if I feel sorry, got something in my throat today. I don't know if I feel like there's a particular piece of legislation that I can point to that I think strikes like a perfect balance. There was a lot of talk recently about a bill proposed by Senator Schumer in the U.S. About regulating AI, and I think in addition there was also a lot of talk about a bill called SB 1047 in California that had something to do with regulating AI systems and they wanted to define like a specific amount of compute that have been used to train these systems. I haven't been like keeping up with a lot of these developments over the past week, but this was a little bit troubling in that there are different ways you could kind of mess with, like the moment somebody says, as soon as a language model gets this large and has these properties, then we're going to regulate it in this way. Somebody can look at that and be a little bit adversarial about it and say, okay, well, I'm going to train a smaller model so that anything larger than it gets regulated or something of that sort. So there are kind of different ways that I feel like these regulations can be gamed. And so I don't know if I feel like anybody has come up with the best solution yet. When it comes to like definitions in particular too, I was thinking about, I guess I spoke to somebody who worked on the AI Bill of Rights, Suresh Venkata who's this professor at Brown University. And one thing that kind of came up in my conversation with him was, does it even make sense to have a specific definition of AI and the regulation you're going to propose? And from what I recall, his stance was maybe not. And that's precisely for the reason that it's kind of difficult to define it in a way that does all of the things that you need it to do. And as protocols need to be sufficiently evolvable over time, if your protocol includes a definition of AI, that needs to evolve, especially if AI completely changes over time. So this is a bit of an unsatisfying answer, I suppose. I don't feel like we're there yet. I feel like there's a lot of experimentation that needs to happen. I'm personally not a regulator, so I won't pretend that I have all of the expertise on this, but I think there's lots of people taking shots. And we're definitely not quite where we want to be yet if we want to do regulation.
Yeah, sounds good. Thank you.
In a sort of related topic, we have a question from Day asking, curious in general about how an agent-centric approach might preclude the necessity for top-down regulations.
I'm not familiar with the personal digital agent protocol. That's an interesting question. I want to make sure I like completely understand what's actually being asked before I go too deep into this, but is what's being said that top-down regulation, I don't know if Day could like comment further or something about this, but if I'm interpreting the question correctly, it sounds like you're asking something like if we had, I don't know, a bunch of different like distributed autonomous agents instead of like big monolithic systems like LLMs, then those smaller systems that where there's more kind of individual small level responsibility, then maybe we don't need top-down regulation on those sorts of systems. That's what I take Day to be asking, and maybe I'll answer that question unless there's a way he can like clarify further before I go on.
Cool. Maybe we can wait for a moment and let another question hop up and see if Day will clarify a little bit in the comments here. Got a question from Dorian about architectures. Are there any others besides transformers that are massively parallelizable?
Yeah. So I think that, so for example, the kind of big competitor to transformers right now is something called a state space model. And I'm not an expert in these. I don't know like all of the math behind them, but they are a system that do have pretty good properties when it comes to parallelization. And they seem to be pretty strong competitors with LLMs on language modeling. Now, this is kind of based on the benchmarks we have so far and the different versions of them. But yeah, that's one example. When it comes to parallelization, again, this isn't like a transformer unique thing. So even convolutional neural networks, for instance, they do a lot of repeated computation. So I was kind of mentioning this aspect of translation and variance, and this is because the convolutional neural nets are based on this operation called a convolution, which basically takes a matrix and then you have like your image, and it applies the same operation to every patch of the image that matches the convolution kernel. The image stays the same when you're doing that. So you can actually take all of those different operations and parallelize them. You don't need to do them in a sequence, for instance. So even the architectures we had before transformers were pretty parallelizable. And that's Not just like some magic, right? That's kind of how you define the algorithm. So yes, plenty of algorithms out there.
Awesome. And yeah, some clarification from Day. I think your take on the question was accurate, but more accurately looking at distributed regulation rather than sort of like the top-down regulation.
Interesting. Okay. Yeah. Okay. Let me try to make that a little bit concrete because I think that's an interesting point. So I guess your point here is that maybe this obviates the need for top down because lots of people are going to have distributed versions, like maybe small versions of an LLM or like a personal assistant or something like this, that they can use as opposed to one big LLM that everybody is using. That's an interesting picture of the world. I feel like there's a lot of people who feel like that's maybe a better version of the world than one where everybody is using GPT-4. But when it comes to interacting with regulation, I don't know that I don't know if I'd go so far as to say it obviates the need for regulation. Maybe. I do think it makes regulation hard, right? Because if everybody kind of has their own little system and can do whatever they wish with it, then if you're going to define things like transparency requirements, disclosure requirements, that does seem to get a little bit hard. I suppose when I'm thinking about obviating the need for regulation, what I'm looking for is, can we ensure that these systems are used in kind of safe ways and relatively like quote unquote good ways for some definition of good? And yeah, I don't know if you think that these systems themselves are intrinsically safe, and that people can generally be trusted to do things with them that are not absolutely terrible for other people and for society, then yeah, probably obviates the need. But I feel like there's maybe some intersecting questions there to work out. I'm sorry, I feel like I probably can't do like full justice to your question in the minute it seems like we have left. Do feel free to email me if you have like further thoughts or one further thoughts on that.
Cool, thank you. One last question here from Evan. The question is, how are these like publicly available systems choosing the topics that are off limits, things like crime, sex, self-harm? What's the protocol for how these topics are chosen, and how does user autonomy balance against social engineering here?
Really good questions. Yeah. So publicly available systems, I take you to mean something like GPT-4 and what it can and cannot discuss. This is like a combination of things. And so, of course, we do have certain laws, of course, about what systems on the internet like can and cannot put out there, and so that places some level of prescription here. When it comes to the protocols, like I think as with social media, I don't know that there's really a fully specified set of protocols. So OpenAI or Google, for instance, they internally are going to make decisions about what GPT-4 can and cannot say, how it can and cannot say things. And the decisions that led to it being that way, those aren't exactly publicly observable. You and I, presumably, I'm guessing you don't work for OpenAI. I don't work for OpenAI. And so I don't exactly know how those decisions got made. Do they have a strict protocol for this? I'm not entirely sure. So I don't know if there even is a protocol for how those topics are chosen. And I think that's kind of important. And so the other question, how does user autonomy, I think that's running off the screen. If you could repeat that for me.
Yeah, how does user autonomy balance against social engineering?
Against social engineering? Yeah. I assume by social engineering you mean just let me understand that. So again, user autonomy is like I can use my system for whatever purposes I might want. And I assume by social engineering you're thinking about how does that come into play with I'm going to interact with other people and I might be able to do or have certain affordances when I'm like using an LLM in my, I don't know, everyday interactions, everyday engagements with the world is how I understand your question. And feel free to let me know if I've kind of misunderstood it. But I think that's yeah, that's a hard question, and I feel like that's hard because it also maybe boils down to your thoughts on like questions about autonomy, maybe how libertarian you are, for instance. And I don't know that a world in which AI systems are going to come into play when we interact with other people. I don't know that it changes the fact that there are fundamental commitments that are going to impact some of these questions. I think that doesn't totally answer your question. And I think that doesn't totally answer your question because I feel like there's a lot of other questions I'd probably have to answer to give you a clear answer on that one. But hopefully that gives you a sense of like how I would start to think about it.
Great. Thanks for all your time here today, Daniel. Appreciate your time and the insight you've given us into the things that you've been looking into. And for everyone else, we'll see you in 2 weeks on June 12th for a chat with author Qifeng Chen. Thanks again, everybody.
Thank you.
Thanks, Daniel.
Thanks.